Every time you look at a camera, it's not just seeing you. It's measuring your face to guess your emotions. That smile you just made. AI already turned it into data, compared it to millions of faces, and predicted your emotion. AI doesn't understand feelings. It tracks angles, distances, and tiny muscle shifts, then guesses what emotion matches the math. The journey begins when photons bounce off your face and enter a camera lens. This isn't passive observation, it's active interrogation. The camera, often a humble webcam or smartphone sensor, becomes the AI's eyes. It doesn't see as humans do. Instead, it records a mathematical representation of light intensity values across a grid, typically 1920 by 1080 pixels or more. Each pixel holds 3 numbers representing red, green, and blue, RGB, intensities. The AI's first challenge: find meaning in this sea of 2+ million numerical values. The camera's curiosity is programmed, a relentless search for patterns amidst visual noise. Employing a Haar cascade classifier or, more commonly today, a convolutional neural network, CNN, the AI scans the image with what we might call digital intuition. It looks for fundamental face patterns, the relatively darker regions where eyes might be, the brighter vertical bridge of a nose, the ovalish contour. It's performing millions of calculations per second, asking at each potential location, does this patch of pixels statistically resemble what I've learned a face looks like? This isn't about recognizing you, it's about identifying the category human face versus background. Once a face candidate surpasses a confidence threshold, the AI draws a bounding box, a rectangular digital fence around the detected region. Everything outside this box is discarded from emotional analysis. The coordinates of this box, x, y, width, height, become the new universe for the algorithm. This step is crucial for computational efficiency and focus, ensuring the system isn't distracted by emotional-looking clouds or tree bark patterns. Here, the AI becomes a surveyor. Using models like Glib's shape predictor or multitask cascaded convolutional networks, MTCNN, it places 68 to 72 precise, invisible coordinates on your face. Points 1 to 17, jawline contour. Points 18 to 27, eyebrows, 6 per brow. Points 28 to 36, nose bridge and tip. Points 37 to 48, eyes, 6 per eye, outlining the orbital socket. Points 49 to 68, lips, 20 points outlining both inner and outer contours. These points don't just sit on the surface, they map the underlying musculoskeletal structure that creates expressions. The geometry of you measuring the symphony. The AI transforms your face into a mathematical symphony. It calculates Euclidean distances between eyebrow points for furrowing between lip corners and nose for smile extent. Angles of eyebrow slant, mouth curvature. Ratios, eye aspect ratio, degree of eye openness, mouth aspect ratio. Facial action units, it identifies combinations that correspond to the facial action coding system FACS, a human-developed taxonomy of facial movements. For instance, $12 lip corner puller plus $6 cheek razor Duchenne smile indicators. The gray canvas, stripping color, revealing form. Color information, RGB, is converted to grayscale. Why? Because early emotional expression analysis revealed that color provides minimal additional information for emotion detection while tripling the initial data. Emotion manifests primarily in shape, texture, and shadow, all preserved in luminance values. This simplification makes subsequent computations dramatically more efficient. Shadow and light, reading the microtextures. Using local binary patterns, LBP, or Gabor filters, the AI analyzes microtextures invisible to casual observation. The specific pattern of crow's feet wrinkles when genuinely smiling. The forehead furrows when concerned. The subtle bulging and tightening of skin around the eyes and mouth. These algorithms detect directional gradients and repetitive patterns at multiple scales, creating a texture signature for each expression. The normalization ritual, the universal face. Your face is mathematically warped into a standard frontal view using affine or projective transformations. This compensates for in-plane rotation, head tilt. Out-of-plane rotation, turning left/right, looking up/down. Scale differences, distance from camera. The landmarks serve as anchors for this warping. A smile detected at a 45-degree profile view is transformed to appear as it would face on, ensuring consistency with the training data. Feature extraction, the neural digestion. Your normalized face enters a deep neural network, DNN, typically a CNN. Imagine this as a digestive system. First layers detect simple features, horizontal edges, eyebrows, vertical edges, nose sides, diagonal edges, smile lines. Middle layers combine these into compound features, eye shapes, nostril flares, tooth exposure. Deepest layers recognize holistic patterns. This combination resembles the prototype of surprise I've seen before. Each layer transforms the representation, moving from pixels to edges to parts to expressions. The statistical ghost, comparison to the average. The system references a mean face, a mathematical average created from thousands of neutral expression faces across demographics. Your facial landmark positions are compared to this neutral baseline. How far has your eyebrow moved upward from average? How much have your lip corners stretched laterally? These deviations from neutral are quantified as numerical feature vectors. The emotional dictionary, the library of expressions. This is the AI's education. It's training on massive datasets like FER 2013, EffectNet, or CK+, containing millions of labeled images. Each image is tagged with ground truth emotions, often validated by multiple human annotators. The AI doesn't understand happiness as an experience, it learns that certain geometric configurations correlate with the label happy in its training data. Pattern matching, finding your family. Using classification algorithms, support vector machines, random forests, or neural network classifiers, your facial feature vector is compared to clusters in the training data. The system asks, which emotion cluster centroid is closest to this face in multidimensional feature space? It's essentially finding which pre-learned pattern family your expression belongs to. The probability game, the confidence spectrum. Instead of a binary decision, the system outputs a probability distribution across emotion classes using a softmax function in its final layer. Your expression might yield joy, 0.72. Surprise, 0.18. Neutral, 0.07. Other, 0.03. These probabilities sum to 1.0, representing the system's relative confidence across possibilities. Temporal context, the story unfolds. In video analysis, the system employs recurrent neural networks, RNNs, or long short-term memory, LSTM, networks to understand expression dynamics. Speed of onset, how fast did the smile appear? Duration, how long is it held? Offset, how quickly does it fade? Microexpressions, fleeting 1/25th to 1/5 second expressions that may reveal concealed emotions. A sudden eyebrow raise followed by sustained widening of eyes tells a different story than a slow, deliberate raising. Cultural and contextual caveats, the nuance layer. Advanced systems incorporate contextual embeddings. Demographic priors, recognizing that expressiveness norms vary across cultures. Scenario awareness, a fear expression during a horror movie versus a job interview has different implications. Personal baselines, some systems track an individual's neutral baseline over time for personalized analysis. This layer is the frontier of emotion AI, attempting to bridge the gap between universal expressions and cultural display rules. The confidence check, metacognition. The system evaluates its own certainty using confidence metrics and entropy calculations. High entropy, probability spread evenly across many emotions, triggers a low confidence flag. Factors reducing confidence include poor lighting creating excessive shadows, partial occlusions, glasses, hands, hair, extreme head poses beyond training data parameters, expressions that don't cleanly match any trained category. Decision threshold, the gatekeeper. A practical threshold is applied, often 0.6 to 0.7 confidence. If no emotion exceeds the threshold, the system may default to neutral or uncertain. In sensitive applications, like monitoring driver alertness, thresholds might be lower to err on the side of caution. In social media filters, they might be higher to avoid false positives. The output, data, not judgment. The result is a structured data object. JSON. Timestamp, May 27, 2024 T 14 hours 30 minutes and 22.125 seconds Z. Face_ID, frame_4221_face_03. Dominant_emotion, joy. Emotion_breakdown. Joy, 0.72. Surprise, 0.18. Neutral, 0.07. Anger, 0.02. Sadness, 0.01. Confidence, 0.72. Bounding_box, x, 422, y, 188, width, 145, height, 145. Landmarks, x1, y1, x2, y2. x68, y68. Dynamics. Onset_speed, 0.25. Apex_duration, 1.8. Offset_speed, 0.42. This data triggers downstream applications. Content recommendation, a streaming service noting delighted expressions during comedy scenes. Mental health monitoring, a therapy app tracking depressive symptom progression. Automotive safety, a car detecting driver frustration or drowsiness. Market research, analyzing real-time consumer reactions to product displays. Accessibility, helping nonverbal individuals communicate emotional states. The epilogue, a mirror with limitations. The process completes in 100 to 300 milliseconds, ready for the next frame. But critical caveats remain. This is not emotion detection, it's facial expression analysis. The AI detects muscular configurations associated with emotions in its training data. It cannot distinguish a genuine smile of joy from a polite social smile. Fearful surprise from delighted surprise. Cultural differences in expression norms. Individual idiosyncrasies in emotional expression. The map is not the territory. The algorithm creates a mathematical representation of facial geometry and texture that correlates with emotional labels. It doesn't access subjective emotional experience. A person may feel sadness while smiling or joy while crying. Bias perpetuation. If trained primarily on Western expressions, the system may misclassify expressions from other cultural contexts. If trained on young faces, it may perform poorly on elderly faces with different skin texture and mobility. Privacy implications. This technology creates permanent records of inferred emotional states, raising profound questions about consent, surveillance, and the right to emotional privacy.